So the polynomial space that we're dealing with are all the polynomials of degree less than 3. So we're dealing with polynomials that, so something in here, polynomial space of degree less than 3 are the polynomials that have this form. Ax squared plus bx plus c, right? These are all the polynomials of degree less than 3. So they look like quadratics. They could be linear or they could be constants. And so there's something that I discussed, that something about the standard basis of P3. And there were these polynomials, the polynomial, the constant 1, that's the one polynomial, the polynomial of a variable just x, and the polynomial of just x squared. So there, you can consider these as the elements that make up any polynomial in this space, right? Because you see we have an x squared term, we have an x term, and we have a constant term. And so then what we try to do is now we say, wait a minute, this can be thought about. Like we can think about our polynomials in degree 3 and P3 space. We can treat them as vectors. So each of these polynomials have coefficients for a, b, and c. And so we can treat each of these polynomials as vectors. That's really that's really the connection you have to make. A lot of these different spaces that we're now going to be dealing with, we're going to revert them back in some way, somehow, to vectors. And so the first standard basis vector, we can treat it as E1. We can treat the second vector as E2, and we can treat the third standard basis polynomial as E3, as the vector 0, 0, 1. So once we have that connection, right, we can see what's the polynomial, so first we're given the rule for the transformation. We take any polynomial in P3, which looks like ax squared plus bx plus c. This is our input in our transformation. And the result is this strange rule, which is that we get a new polynomial, but now the polynomial has this form. The coefficient of x squared is 2a plus b. The coefficient of x is 5a plus 5b plus c times x minus a. So this is a rule that was defined. So this is the definition of t. So this is the definition of t. And what we want to do is to find our goal. What's our goal? Is to find t inverse. I want to know what t inverse is. I want to know what it is. What is the transformation that takes my range and gives me back the element in the domain? So what is that? What is that transformation that reverts back or that undoes this rule? So to do that, I first need to find, so first find the standard matrix of T. That's the first thing I need to do. First find the standard matrix of my original transformation. And how do I do that? I multiply the standard basis vectors. Remember, I'm treating the standard basis polynomials as vectors, right? Because 1 in P3 is the same thing as saying what? This is the same thing as saying 0x squared plus 0x plus 1. This is the same thing as saying x is the same thing as saying 0x squared plus 1x plus 0. And x squared is the same thing as saying uh 1x squared plus x, 0x plus 0. That's what we can treat them as. And so given this connection between ax squared plus bx plus c and the first entry of the vector being the first coefficient, the second entry of the vector being the coefficient in front of x, and the last entry in the vector being the coefficient of x squared, if I treat it this way, then I can write each of these polynomials individually as e1, e2, and e3. I hope that makes sense. So then I can treat it like this now. I can plug in TE1, right? And this becomes T of 0x squared plus 0x plus 1. And when I do that, I just have to apply the rule that I'm given. This is the rule, right? I take 2, multiply it by 0 plus 0, x squared, plus 5 times 0 plus 5 times 0 plus 1, x minus 0. So what's the result? The result is a polynomial that looks like this: 0x squared plus 1x plus minus 0 or plus 0, which as a vector would be what? 0, 1, 0. That would be my first column of my matrix A. Remember, this is the first column of A. Why is A and B 0 in this case? So that's the question, right? Again, I'm don't forget the general idea. I have a transformation, whatever that is, right? It takes something in one vector, it's going to be called a vector space. So it takes something in the domain of this transformation and takes it to the range. Now, because it's a linear transformation, we can use a matrix to represent that same transformation. So we have this transformation that's defined in this very strange way. It's a linear transformation, so I can find a matrix that's associated with this linear transformation. Now, in this world that we're living with, that we're living in currently, P3, they're all the polynomials that look like ax squared plus bx plus c. Every polynomial that's in here looks like this. And what you have to make now is the connection that this polynomial can be treated as a vector, where we take the coefficients of my polynomial, which there's only 3 of them, and treat those coefficients as the entries of a vector. So that's another way we can treat a polynomial of this kind is as a vector. We can treat them as vectors now. So then the smallest elements, you can think of it, the smallest elements of these polynomial space, in this polynomial space, are the polynomials that look like these 3 polynomials here. We have a constant, we have a term that only has an x in it, and the term that only has an x squared in it. Any linear combination of these 3 polynomials creates a polynomial in this space. That's the idea behind a basis. We'll talk more about bases later. It's like a little intro to that. So if this is the case, that this is represented as a column vector, and this is a polynomial in this form, right, which is 0x squared plus 0x plus 1, this here, with this connection with the coefficients of the polynomials, can be treated as E1, 1, 0, 0. This polynomial can be treated as 0, 1, 0, and x squared can be treated as 0, 0, 1. Does that make sense? And so then when I plug in E1, I'm plugging in a polynomial that has A being 0, B being 0, and C being 1. And then I just apply the rules that I see. Then the result, the image of E1 underneath this transformation, gives you a polynomial of this sort. And it's 0, 1, 0. And then what's TE2? It's T 0x squared plus 1x plus 0. This is what? 2 times 0 plus 1 x squared plus 5 times 0 plus 5 times 1 plus 0, x minus 0. And what am I left with here? I'm left with just a 0. No, I'm left with a 1x squared plus 5x minus 0. the vector would look like 0, 5, and 1. So that's my second column. This is my second column of the transformation of the matrix A that represents T. And then finally, this is 0x squared plus 0x plus 1. So this would be what? 2 times 0 plus 0x squared, 150. The reason why it's not 150, it's because I defined the vector to be of this form, where the first entry is the constant, the second entry is the coefficient of the linear term, and uh, the last coefficient is the coefficient of x squared. So if I would have reordered that, if I would have called this A, B, C instead, which is more natural, right? Then this would be this one would be E3. This would be 0, 0, 1. This would still be 0, 1, 0, and this would be 1, 1, 1, 0, 0. This would be E1 instead. Do you see that? So because of that reordering, this would be a little bit different. The transformation in itself will still be the same. It's just that the order of things are just switched. And the reason why I did that is because normally this is E1. That's all. Yeah, normally this is E1. But again, it doesn't matter at the end of the day. It doesn't matter. As long as you're consistent with the ordering of what you started with, if you're consistent with this, and then that if you're consistent with the way you represent these standard bases, then everything will be just fine. So as you can tell, the ordering of things does affect the visual of the matrix representation, but it doesn't affect the overall answer at the end. It doesn't, as long as you're consistent. But that's a very keen observation, because it's a little weird, right? That this will be 0, 5, 1. And normally you use this number, you see that this is 1 first, and then you see the 5 and then the 0. But it's just the way I ordered it from the beginning. And then we get this to be what? 5 times 0 plus 5 times 0 plus 1, right? 5, yeah, x, and then minus 0. So then what's this here? This is 0, 1, 0. And this is my third column. So then once I have those three columns, I have my matrix A, right? X squared 2AB. Wait, let me see, E3, right? 1x. Oh, that's my mistake. Pardon me. That's right. I wrote this incorrectly. Sorry, this should be 1x squared plus 0x squared plus 0. That's going to change things. That's why also I saw this a little bit strange. How did this came up again? So this should be 2 times 1 plus 0. This should be 5 times 1 plus, let me see, 5 times 1. Yeah, 5 times 1 plus 5 times 0 plus 0 minus 1. So that should be, yeah, this should be 2, sorry. This should be 2x squared plus 5x minus 1. So the vector would look like -1, 5, 2. Shouldn't there be a 1 at the end? No, the 1 is the end is the a value. Remember, it's the a value. The a value is associated with the x squared. So the a value here is 1. The b value here is 0, and the c value here is 0. That's why when you plug it in, you get -1 at the end. Does that make sense? So then the vector would, remember the vector representation of my polynomial starts with the coefficient, the constant first, and then the linear term coefficient, and then the x squared term coefficient. So that's why this is the constant term first, -1, and then 5, and then 2. Because of that, the ordering from the beginning. Okay. So then, does that make sense? So then the representation of T, the matrix representation, is given by the first column being a 0, 1, 0, second column being 0, 5, 1, and then the last column being a negative 1, 5, 2. And so then that represents this represents the polynomials from CBA to A, right? But now I want to find now the inverse. So I want to take something from the result and I want to get it back. So how does that look like? So if I call this another polynomial, right? We use different letters, d x squared plus e x plus f. I want to get back my polynomial. So what do I get? What do I have to do to get the inverse? I just take the inverse of my coefficient matrix and I would get back. So this would be FED and I would have to get back CBA. So in essence, all I'm doing is figuring out what the inverse is. And you can use your calculator for this. I don't have one at the moment, but let me just get a calculator. So here I have a calculator. I can put this in my matrix, second matrix. And then I can edit. So I got 0, 0, 1, first row. Second row is 1, 5, 5. I got 0, 1, 2. Boom, I got
The
my
first row's third entry is a -1.
Oh, you're right. You're right. Thank you. That's right. -1, right? Thank you. So then we go to math. No, we go to fresh start here, and then we have second the matrix. Put A. Take negative of -1, which in this case would be the inverse, and that would be my inverse. So I have the inverse is -5, 1, -5, 2, 0, 1, 1, 0, 0, -1, 0, 0. And this will be the representation, the matrix representation of the inverse. It will be the inverse. Okay, so we have the inverse here. So that means that every single time now when I have a new polynomial, T inverse, and in this case, guys, I know it seems kind of weird to do this, but I can just rewrite it as ax squared plus bx plus c. Like these letters at the end of the day, they're not significant. I can rewrite them like this. I can take another polynomial, ax squared plus bx plus c. What does it do to it? What does A inverse do to it? It takes -5, 1, -5, 2, 0, 1, and -1, 0, 0. You apply that matrix A inverse to it, and this is going to be, again, in this order that I had from the beginning, CBA. So then when I apply the matrix multiplication, I get -5C plus B minus 5A, and I can rearrange that to look like A, B, C first, like the ordering. This would be 2C plus A, and this would be -C. So then what does the inverse do to polynomials? So the first coefficient of the polynomial will look like -5A plus B minus 5C. That would be the coefficient of x squared. No, pardon me. That would be sorry, the coefficient of x squared would be negative c because we start this, right? We started from here. This is x squared, this is x, and this is constant. That's the way we defined it. So this would be, so negative c here is the coefficient of my image x squared. Then the next coefficient would be a plus 2c. That would be the coefficient of x. And then my constant would be negative 5a plus b minus 5c. And you can also write it this way as no, it's the way, yeah, you can leave it like this. So this would be it. This would be the rule for my inverse. And the idea is, as long as you understand that the inverse transformation is just the inverse of the matrix representation of the original transformation, then you should be okay with figuring out what the rule of the inverse is. So any questions about this? This is a little strange example. It is. And we'll talk more about bases of different spaces a bit afterwards, after the first exam. But this was just a little introduction to that whole idea. Yeah, exactly. And that's the reason why I'm going over this, just in case, for those of you who are having that problem on the homework, because that homework is almost identical to this, the finding the inverse transformation from P3 to P3. But the idea hasn't changed with finding the matrix representation of a matrix, and then all you have to do is one more step is the inverse of that matrix, and you guys are know how to find inverses. Okay. All right, guys. So we're good with. I hope so. We're good with linear transformations and how matrices are represented by them. I don't know how to input the answer. So Leo, you can email me about that, okay? And particularly which answers are you speaking of? Because I don't know which one you're talking about, which problem you're speaking of in terms of inputting the answers. So for different questions, you have different ways to input. So if you have a particular question with that, please email me and I'll get back to you. Okay. All right, guys. So thank you, Leo. So for now, the rest of your homework assignment, right, has to deal with determinants. So we're going to be talking about determinants extensively today. It kind of feels like we're going from theory to application, like quite, like almost like every 2 lectures is theoretical and then all of a sudden it's very applicable. So in this case, there's a lot of computation involved with determinants. And then we'll eventually see there's a lot of theory behind determinants as well. It's not just a number, but for now, it seems like you're just computing numbers kind of like arbitrarily. So the first order of business is to understand some terminology. And to start, we're going to talk about what a minor is and what a cofactor is. So we have two things. We have a minor and a cofactor. So what is a minor? So a minor is the determinant of the submatrix. And you'll be like, wait, how do you define a determinant without using the word determinant? That's kind of funny, right? But the idea is this. So the minor of AI, A sub ij, so the minor of entry A sub ij of your matrix is equal to the determinant of submatrix of matrix A without row I and without column J. So that may seem a little strange, and we denote this, it's denoted by the symbol MIJ. And then we have the cofactor. The cofactor is the determinant, is negative 1I plus J of the minor IJ. Mirror, like the cross product. Yes, when you do the cross product, you do apply what's called the determinant. When you do the cross product of the two vectors, right? You put I, J, K, and then you put the vertices, the entries of the vectors themselves in rows, and then you perform what's called the determinant. And that gives you the cross product. The result is the cross product. So yes. So what in the world are we speaking of? When I say, so look at the first example. So when I'm looking at this matrix A, and I want to figure out what M13 is, and then I want to figure out what C13 is. When I want to figure out M13, I go to 13. What is 13? 13 is this entry here, right? First column, first row, third column. And what I'm going to do is I'm going to strike out the first row and the third column. So M13, it would be the determinant of the new matrix, of the smaller matrix, which would be what? 2, 2, negative 2, 4, 1, 0, 2, 10, 2. And when you have just a straight line, instead of a bracket, instead of a parentheses, when you have straight line, it looks like absolute value, that's the determinant. And then I can find the determinant of this by what we'll see later, by cofactor expansion. But this would be the M13. And then what is C13? C13 is negative 1 raised to the 1 plus 3 times M13. That's all it is. It's the same thing as the M13. It's just going to either be a plus 1 or it's going to be a minus 1 attached to it. So in this case, 1 plus 3 is 4. Negative 1 to the fourth power is positive 1. So C13 in this case is the same thing as M13. It will be the same thing as M13. Okay. And then what is M33? What would be M33? So then you look at the matrix again. You look at what's entries in the third row, third column, right? We strike out the third row and the third column at once, and then that new matrix, that's going to be finding the determinant of that new matrix, 3, 3, 5, 2, 2, negative 2, and 2, 10, 2. If I take the determinant of this matrix, then I get the minor. And the same thing goes for C33. Now I got negative 1. I got 3 plus 3 instead, because that's my IJ, right? My IJ. 3 is my I, the ith row, and this 3 is my jth column. I'm just plugging it into the formula. So again, it becomes more formulaic. And then negative 1 to the 6th power is positive, right? So this is C33. In this case, also equals M13. M33, pardon me. So we're going to discuss a little bit more what it means to actually perform determinant. Like, how do you actually find a determinant? But for now, I just want to make sure we get that clear, what a minor is, and then what it kind of, it, so the cofactor is a whole matrix. No, the cofactor is the determinant of a matrix. So the cofactor here, the cofactors are in relation to every entry of a matrix. So that's why we have C13. C13 is the product of -1 raised to the I plus j power times the minor of entry A13. And what's the minor of the entry of A13? It's the determinant of the smaller matrix when you get rid of the first row and get rid of the third column. So that would be this matrix, but that's the determinant of this matrix. So then so this, in a way, I'm defining minors and cofactors recursively, right? I'm using the word determinant to define what the determinant is. So I'm finding the determinant of a bigger matrix by finding the determinant of a smaller matrix. So that's where we're heading with that. So we get back to like the base, and then it's kind of like recursion. I don't know if I'm making that connection with you guys, but you'll see what I mean. So now the same thing happens with this bigger matrix. What's the minor of the entry 3, 2? Look, go to the third column, second row, this number here, right? That would be the entry 3, 2. What am I going to do with this? I'm going to strike out the third row, second column, and then I'm going to find the determinant of the smaller matrix that I make by getting rid of that row and column. So M32 would be the determinant, and again, I'm using the straight lines to denote determinant, would be 4, 0, 1, 0, 3, 3, -1, 0, 9, 6, 2, 3, and 2, 4, 2, 3. And then what would C3 be? C32, what would be the cofactor of the entry 3, 2? It would be -1 raised to the 3 plus 2 power of the minor 3, 2. But 3 plus 2 is 5. -1 to the 5th power is negative. So C32 would be negative M32. And that's how this goes. That's all this is doing. I'm getting the determinant of a smaller matrix, and then the cofactor would be either negative or positive of that determinant. Okay. And then that's C3. And then M41, gonna go back to the drawing board here. For 1, I go to the 4th row, first column. This is gonna get rid of the 4th row and the first column. And so then the matrix, the determinant would be 0, 0, 1, 0, 3, 3, -1, 0, 2, 4, 2, 3, 2, 4, 2, 3. And then C32, sorry, C41 is -1 to the 4 plus 1 times the 41, right? The minor 41. 4 plus 1 is 5. -1 to the 5th power is -1 times M41. So it's just negative. Okay, so far, those are what cofactors and minors are. Okay, we haven't really defined what a determinant is as of yet, but we know that to find a determinant, we need to use minors and cofactors. And what's the minor? It's a determinant of that smaller matrix, dependent upon what entry you're using. Okay, so that's what the cofactor and minor is. Yes, Sam.
So just out of curiosity, is this leading to, since we know determinants of 2 by 2s only, we just continue going further down?
Correct. Correct. Correct.
Got
Yes, that is right. So then now the next order of business is, wait, what do you mean? Wait, why do we even need minors and cofactors to begin with? So to find a determinant, we use what's called the cofactor expansion. And what we do is we go along either any row you'd like, or any column you'd like of the matrix, and we perform what's called a cofactor expansion. So then the determinant actually, the determinant of A, if we say the determinant of A can be found by performing what's called a cofactor expansion. And the cofactor expansion is the following. I take I'm sorry. I take 1j, C 1j plus A 2j times C 2j. I do this all the way to A nj times C nj. So what is this here? I know it's right now it's just going to be notation, and then you'll see what I mean by this. This is the summation as k, I should say I goes from 1 through n of aij multiplied by cij. This is the cofactor expansion. This is what's called the cofactor expansion along the jth column. So you can go along one column and find the cofactor for every entry along that column. Find it, which we know how to, which we'll find how to find that. And then you can multiply each of those entries by the cofactor, add those up, and you get to what's called the determinant, where j is constant. Yes, j is constant. I'm selecting the jth column, whatever that column is, and I'm just going through the entries along that column. That's one way to define it. That's one way to define it. Another way to define it, so I should write like this, is if I go along a row. So then in this case, the I would be constant. So it would be A sub I1, C sub I1 plus A sub I2 times C sub I2 plus dot all the way to A sub I, sorry, yeah, A sub I n times C sub I n. This is a summation as j goes from 1 through n, and this is aij times cij. Okay, and this is the cofactor expansion along, sorry, let me write this a little bit clearer, along the ith row. So what's cool about the determinant is that it doesn't matter which row or which column I use, as long as I'm consistent. Wait, do you guys see this? Or is it frozen?
Oh,
Okay,
it
there we
just
go.
showed up.
Yeah, it froze a little bit. So what's cool about the determinant is that it doesn't matter which row I choose, nor which column I choose. As long as I perform this, what's called cofactor expansion, I get the same value again and again and again. And so what you'll see is that there's certain rows and columns that make more sense to use, or in terms of the convenience in the computation to use rather than others. So for example, I wouldn't perform cofactor expansion along the first row, the first column, nor the second column, because I have all of these numbers are non-zero. So one technique is to find the row or column that has a lot more zeros than, or out of all of the rows and columns, which one has the most zeros entries? Because then the computation becomes much simpler. So in this case, it kind of seems kind of apparent that we should go along the third column. Now, what does that look like if I go along the third column? Well, that means that I'm going to take, and if I apply the formula, right, I'm going to take what? I'm going to take A1. Yeah, I'm going along the, yeah, so it'll be A1 3 times C1 3 plus A 23 times C 23 plus A 33 times C 33 plus A 43 times C 43. Okay, that's what I'm going to be doing. I'm going to find the first entry along that column, multiply by the cofactor of that first column, of that first entry in that third column, and then so on and so forth. But what's nice about A13? A13 is what? 0. So what happens? This guy goes away. And then what happens with A23? It's also 0. So you see how my computation here, I just got relieved because I don't have to do these anymore. It becomes 0. So all I really worry about is A33 times C33 plus A43 times C43. That's all I really care about. Okay, everybody with me with this? I'm applying the formula for cofactor expansion along the third column of matrix A. So I know what A33 is, right? This is -3 times C33. And what's A43? This is 3, C43. So really, in reality, what I really care about is C33 and C43. That's what I care about. What's the formula? Well, I have to take -1 of 3 plus 3, multiply by the minor of M33, and then take C43. I need to find -1 to the 4 plus 3 power times the minor of 43. So far, so good. 3 plus 3 is 6. -1 to the 6 power is +1. So C33 is really just M33. And this would be -1. So this would be negative M43. Now, what is M33? Well, M33 is the determinant of. So if I do this, what do I get? I get 3, 3, 5, 2, 2, -2, 2, 10, 2. This is the determinant that I need to find. And then what's negative M43? It'll be negative M43, and now I have to do put this one down here. This becomes 3, 3, 5, 2, 2, -2, 4, 1, 0. Does everybody see that? Are we good so far with this? Yes, sir. Okay, good. Okay, so now what do I have? I have a smaller matrix, 3 by 3. I went from a 4 by 4 to the 3 by 3. And now the question is, wait, what's the determinant of a 3 by 3 matrix? So you see how this is like kind of recursive now? Because now I'm like, okay, now I can find the determinant of this matrix by the same idea. Apply the same operation for determinant. Either use the cofactors along the jth column or the cofactors along the ith row. Now, because none of these numbers are zeros, there's no real easy way to do this. We're just going to go through it, okay? We're just going to go through it. So I'm going to go through the first row. So I'm going to do the cofactor expansion along the first row. What is that going to look like? It's going to look like 3 multiplied by the pardon me, the cofactor expansion along the cofactor. If I were to, sorry, if I were to start from this entry, I would have to do what? Get rid of these two, right? The first row, first column, and then I'm left with this matrix here, which is it's negative, right? Is that negative? That's just positive. Okay. So then it would be multiplied by the determinant of the smaller matrix, 2, -2, 10, 2. Does everybody see that? Now this is a smaller matrix here. And then go to the next entry. So I'm going around along the first row, right? Go to the next entry. What's the next entry? It's 3, right? Then do what? Eliminate the first row, second column, and I'm left with what? I'm left with 2, -2, 2, 2. This is the determinant of the smaller 2 by 2 matrix. And then finally, the last entry here is a 5. This will be plus 5, determinant of eliminate first row, third column. And I'm left with what? 2, 2, 2, 10. Now, one thing we have to always be careful of, remember, it's not just the determinants. We have to also figure out the sign, because the cofactor deals with the sign and it deals with the entries when you sum up the indices of the entry. So for example, this here was a 1, 1, right? So -1 to the 1 plus 1 is positive. So this is positive. The second entry is 1, 2, right? The indices. So 1 plus 2 is 3, -1 to the third power is negative. So this should be a -3. And then the next entry would be what? 1, 3, right? 1, 3. So 1 plus 3 is 4, -1 to the fourth power is positive. So if you notice, this will be positive, negative, positive. And then what happens here? This is 2, 1, that'll be negative. So it's negative, positive, negative, positive, negative, positive. They just alternate. They're alternating. The -1 with the cofactors just switch on and off. You just have to be careful with the indices. That's all. Does that make sense? And now the question is, how do you find the determinant of a 2 by 2 matrix? What do you guys think? I know some of you already know how to do this, right? You take the product of the diagonals and then you subtract the product of the off diagonals. But see how that's consistent with the definition of the determinant. What's the definition of the determinant? If I just want to find a determinant of 2, -2, 10, 2, what would I do? I would either apply the cofactor expansion along one of the rows or one of the columns. So for example, if I apply across the first column, let's just do that. What would that look like? The first column would be what? It would be 2 multiplied by, and then what do you do? What do you do, guys? You eliminate that. So it's 2 times what? 2. Oh, wait, that makes sense now, right? The diagonals, you're multiplying those entries along the diagonals. And then what happens with the next one? This is 10, right? 10. And then what do you multiply by when you eliminate this? 10. The first row, the first column and the second row, what are you left with? -2. And because this entry here is 1, 1, this is positive. This entry is what? 2, 1. It's negative. I get negative. Do you guys see how that's consistent now with the determinant of the matrix of a 2 by 2 matrix being A times D, which is normally what you say. A, this is D, this is B, this is C. Normally it's AD times minus BC. Do you guys see now the recursive nature behind this? I hope you do. So it's a lot of computation, as you can tell. This becomes -3 multiplied by, now we can go quicker. This is 2 times 2 minus -2 times 2 plus 5 times 2 times 10 minus 2 times 2. All of this now is just multiplication, addition, multiplication, subtraction. That's all it is. It's a lot of it. But then eventually you'll see there's going to be easier ways to do it, especially by 3 by 3. I'll show you a trick for this. So then, to be consistent with this becomes 3. This is what? 4 minus or plus 20 minus 3. This is 4 plus 4 plus 5. This is 20 minus 4, right? 20 minus 4, which is 3 times 24 minus 3 times 8 plus 5 times 16. And then you can put that, if you want, in your calculator just to figure out what those numbers are. So 3 times 24 minus 3 times 8, which is 24, plus 5 times 16. I got 128. What did I just find? I found M33, which equals C33. So this equals -3 multiplied by 128. And now I'm gonna do the same thing for C43. What is C43? So be careful with the negatives, guys. This is negative parentheses. do it across any column, any row. I'll do it across. I'll do it across because I see a zero. I'm gonna use a zero. So I'm gonna do the cofactor expansion along the third column. So what does that look like? It's gonna look like 5 multiplied by C C13 plus, I should say here is negative 2 times C23 plus 0 times C33. But 0 times anything is 0. So I'm really have negative parentheses 5 times C13 minus 2 times C23. That's what I really have. So I really want to find what C13 is. So what's C13? C13 is negative 1 raised to the 1 plus 3, which is M13. And then C23 is negative 1 raised to the 2 plus 3 times M23. And then what's M13? If I do M13, I eliminate this, and I get 2, 2, 4, 1. And this is negative 1 to the 4th power, so it's positive. So this will be 2, 2, 4, 1. Determinant of that should be what? 2 minus 2 times 4, which is 2 minus 8, negative 6. What's M23? This will be a negative determinant. M23, you get rid of the second row, third column. I have 3, 3, 4, 1. 3, 3, 4, 1. Negative of that will be 3 times minus 12. So 3 minus 12 is negative 9 times the negative, it's positive 9. So this is what I have. I got negative 5 times negative 6 minus 2 times 9. Negative 30 minus 18. Sorry, it should be negative 30. Negative 30 minus 18. This will be a negative 48, which would be positive 48. So that is my determinant. So I did it. So the determinant of A is all of this computation. The determinant of A, and of course, I'll post this up. I'll post this up for you guys on Blackboard so you guys can do this on your own for more practice. I'll leave this for more practice for you guys. So the determinant of A, in this case, is this last number here because this number came from the cofactor expansion, right? No, this number is M48. Yeah, this number is the minor of C43. So C43 is 48 and C33 is 128. Let's do some bookkeeping here. And so finally, what's the determinant? The determinant of A originally was negative 3 times 128, which was C33. Now C43 is 48. So then I'm going to compute that. So negative 3 times 128 plus 3 times 48. So the determinant for this number here, so it's negative 3 times 128 plus 3 times 48, and I get negative 120. Why? Okay, so he says, why do we use C13, C23 here? And for the previous C33, why do we use a 335? Okay, so, okay, I know there's a lot of, hold on, let me just divide this up. Okay, so first of all, I'm trying to find what the determinant of A is, right? And so I decided, hey, I'm going to use the third column to apply what's called the cofactor expansion of the determinant of A. Why am I using the third column? Because I see 2 zeros. And why this is good is because I have less computation to deal with. Because the moment I have 2 zeros in my entries, then two of these computations I don't have to worry about them. I only have to worry about these two computations here. In reality, I want to figure out what C33 is, which is a cofactor of the entry A33, and C43, which is a cofactor of A43. Now, what does the cofactor of C33 entail? I need to find the minor of the entry A33, which is just saying, hey, take the third row, third column, and just erase those, eliminate those to create a smaller 3x3 matrix. Find a determinant of this. Now, to find the determinant of this, I have to perform cofactor expansion once again. And again, now, because there's no zeros, there's no clear way which one is more convenient to use. You can use anything you'd like. Any row, any column that you would like to perform the cofactor expansion upon. And I decided just to show you, hey, let's use the first row. Just the first thing we have. The first row, I have the number 3. Then I have the cofactor of that. What's the cofactor of 3? It's the smaller 2x2 matrix. And then I'm going along that same row again. Then now this entry here is 3, but there's a negative because of the cofactor of this guy having a -1 being raised to an odd number because of the 1,2 entry of 3. That's why there's a negative here. And then what's the cofactor of this? I need to find the smaller determinant of 2, -2, 2, 2, right? And then so on. And then with 5, the same thing. I'm using this smaller matrix. Then I find the determinant of this guy, determinant of this guy, which now you guys see why it's AD minus BC. Now you see why we're multiplying these numbers and subtracting them. We're multiplying these numbers and subtracting them. It's because of the consistency of the definition of the cofactor expansion of the determinant. And so I found that this whole thing, yes, Sam, that's right. You want to make it easy for yourself. You always want to make it as easy as possible. So you don't want to choose a row or column that performs more computation than needed, right? So in this case, M33 is equal to C33, which equals 128. So I got this guy good. Now I need this guy. Now I need C43. And it's just to answer your question, Ken. Yeah, it wasn't a specific choice. It's a specific choice because of convenience, not due to the formula. And then C43 is equal to the minor of the negative of the minor of M43. And what is M43? Well, look at the is it 43? Hold on. Yeah, M43. I don't know why I just got a brain for right now. M43 is the fourth row, third column. I don't know. Okay, the fourth row, third column. So you strike away the fourth row in the third column, and then you're left with a smaller 3x3 matrix, right? 3, 3, 3, 3, 5, 2, 2, -2, 4, 1, 0. And the reason why in this problem I'm using the third column is because I have the only column with the 0. I could have used also the third row, then the same thing. But I use this last row, this last column, because there's a 0 in it. So I'm doing the cofactor expansion along this column. Does that answer your question, Ken? And then the C stuff here, is in relation not to the original, not to the original C13. This is related to the smaller C13, the smaller matrix. Do you see that? We're going into, now we're like, forget about this. We're only worry about this now. Now we have submatrices to this submatrix. So C13 is the submatrix when you eliminate the first row and the third column of the smaller submatrix that we just had. Does that make sense? So this C13 is not the same C13 over here. It's not the same. But does that make sense to everybody out there? How to find determinants? Okay. Okay. So I know at first it may seem like this is quite convoluted, right? It's like all this computation just to find a number. And they're like, oh, what does that number even mean? What does it really matter? How did someone come up with this scheme of computing what this number would even actually be. And it's interesting how you do this operation across any row or any column, you get the same number. Pardon me. So let's look at some simpler matrices. And let's look at, for example, triangular matrices. So triangular matrices are really nice because you can find a determinant almost instantly. Now, how do we apply this? So look at all these rows, right? There's one row of, there's one there's one row of zeros. So what do you think the determinant is for this one? Which row or column would be convenient to use to apply cofactor expansion upon? So
First
remember,
row.
the first row. The first row because you have all zeros. Hey, wait a minute. So if you have all zeros, what happens when you apply the cofactor expansion? What do you get? So across the first row, right? So this is first row. Cofactor expansion. What am I supposed to get? I'm supposed to get A11 times C11 plus A12 times C12 plus A13 times C13 plus A14 times C14, right? That's the cofactor expansion formula. But then all these are zeros. So 0 times C11 plus 0 times C12 plus 0 times C13 plus 0 times C14. 0 plus 0 plus 0 plus 0 plus 0, 0. So then you should notice something. So what do we notice? Note, any matrix with at least one row or column of zeros will have a determinant equal to 0. Okay, we just observed this. We observed this fact upon this triangular matrix because one of the diagonals was a 0. So we'll talk about this. So Tostov, you're on the right track with diagonals, but they're not. It's not going to be the sum, and you'll see. So look at the second. Look at the second matrix. So here, what would you perform? Which column or row would you use to perform cofactor expansion to find a determinant? There's two obvious choices here, right? You can either use the first row or the fourth column. So since we already used the first row for the previous example, let's use the fourth column just to see, right? So the fourth column, what is that going to look like? That's going to look like A14 times C14 plus A24 times C24 plus A34 times C34 plus A44 times C44. Okay, so I'm expanding across the along the fourth column. What's nice about this? Well, what's nice about this is that A11, A14, A24, A34 are all zeros. So this is equal to, all of these are equal to 0. So I don't have to worry about that. You see how that's nice? Imagine if I did it along the first column. I'm gonna have to worry about this one, this one, this one, and this one. If I do it along the fourth column, hey, all of these guys, I don't even have to worry about it. I just have to worry about 3. So what's A44? It's equal to 3. So this is equal to 3 times what? C44. So be careful. What is C44? C44 equals -1 to the 4 plus 4 times M44. But what is M44? Boom, boom. It's a smaller matrix. M44 is, so again, -1 to the 4th plus 4 power is going to be -1 to the 8th, which is positive. So what's M44? It's the determinant of -3, 0, 0, 1, 2, 0, 40, 10, -1. And then now the question is, what's the determinant of the 3 by 3 matrix? So which row or column do we do cofactor expansion upon? You can either use the first row or the third column. Do you guys see where this is going? Okay, so now you see it's 6, right? But do you see where this is going now? If I do this, so let me do the third column here, along the third column. Again, what's nice about the third column? I got zeros, a whole bunch of them. So I'm only worried about -1. Now, -1, what's the entry in this particular matrix? This is 3 plus 3, 3, right? So that's okay. So this is going to be a -1 multiplied by, now, look at this. This will be the determinant of -3, 0, 1, 2. This is negative, parentheses, -3 times 2 minus 0. This is +6. So this equals 3 times 6, which is 18. And what's the big idea behind this? If you have a triangular matrix and you want to find the determinant, if you notice, I'm using -1 here, right? This is one of the entries. This is one of the diagonal entries. I started with 3 being the diagonal entry. There's a -1 here, diagonal entry. Then I'm multiplying -3 and 2 diagonal entries. So the note here is that the determinant of triangular matrices is the product of the diagonal entries. So that's really convenient. Because imagine if I'm going to do cofactor expansion every single time, I'm going to lose my mind too. So you see, if I notice, hey, this is up lower triangular. So a whole bunch of zeros on the top above the diagonal. Look at, I just have to worry about these entries. Hey, what happens when you multiply 0 by anything? You get 0. So obviously I'm going to get 0. Look at these numbers. I got 100, 200. You're like, oh my goodness, I have to do all of this computation. No, you don't. If it's a lower triangular, just look at the diagonal. That's it. These diagonal entries, when you multiply them, it doesn't matter. When you multiply them, what do you get? You get 18. Oh, there we go. That's a good comparison. Inception. That's right. But do you see that, guys? So lower triangular matrices, upper triangular matrices, easy. Hey, what's the determinant of this upper triangular? Hey, guess what? Multiply these together. Well, that's pretty easy. 2 times 3 times 100. 600. Done. I don't have to break a sweat. I don't even break a sweat. Imagine having to apply the cofactor expansion along the fourth column. You're gonna be like, oh, like, come on. But you still get the same idea. You still get these numbers here. But now it's quicker. Now here as well, what is the determinant of this? It's 1 times -1 times 7 times 5, -35. Done. Well, Sam, that's kind of what, we do when we teach math, like mathematics. Like we tend to always demonstrate, like either we do two things. We either do something, we do like the simple problems of very complex ideas, and then or we present very large computationally intensive problems at first, and then we show you, oh no, there's a better way. It's like when you first learned how to find a derivative, right? Remember when you guys learned how to find a derivative of function, use the limit definition, and you're like, oh my goodness, you have to like expand all these polynomials, eliminate, subtract, cancel, factor out the h, and then you're like, oh, this is the derivative, and then like, oh no, yeah. So all that time that you've been wasting it on that, you could have just applied the differentiation rules, and you're like, great. So it's kind of like that, and it's sometimes there's no way around it. Sometimes you just have to like go through like the difficulty and then see how easy it is at the end. But anyways, yeah. So triangular matrices, great. They're great, right? Yeah, exactly. The Riemann sum also another thing. Oh my goodness, trying to integrate a function using the Riemann sum every time, you're gonna lose your head. Like eventually, you're gonna lose it. So see, that's what happens a lot in mathematics, and this is no different. But cool. And then guess what, guys? There's another trick. That's right. I told you. There's a 3 by 3 determinant trick. So instead of having to do the cofactor expansion, you're like, oh my goodness, I have to do all this stuff. This is actually a cool little trick. So if this only works for 3 by 3 though. It doesn't work for any other size. So what's the idea behind the 3 by 3 trick? If you have a 3 by 3 matrix and you want to find the determinant of any 3 by 3 matrix, and again, remember we use these absolute value signs. In this, it's not absolute value, but they look like absolute value signs. They represent the determinant. What you do is you locate along the other side of the matrix. You rewrite column 1 and you rewrite column 2. And then what you do is something really interesting is you take the diagonals like this. So these 3 diagonals that you have of 3 entries, you multiply them together. So you get A13 times A22 times A31. And then you multiply these numbers together. And then you do the same thing for this one. A11 times A23 times A32. And then you have, so this is the first product. This is the second product. This is the third product. This is A12 times A21 times A33. So you take those 3 products and you do the same thing on the other diagonal. So then you have the fourth product, the fifth product, and the sixth product. So the fourth product is A11 times A22 times A33. The fifth product is A12 times A23 times A31. And then the sixth product is A13 times A21 times A32. You take those products together, and so the determinant of A actually becomes A11 times A23 times A22 times A33. You take that sixth product, you add it to the fifth product, 1A12 times A23 times A31. You add it to A13 times A21 times A32. And then you do this subtraction. So the diagonals that go from left to right, from the diagonals that you see as the arrows point from upper left to the lower right, these are all products that are positive. And then we look at the other one in the other direction. All these products are going to be, you're going to sum them up, you're going to subtract it. And that's the trick. That's it. My magic trick is done. So I got A13 times A22 times A31. That's one thing. And then you add that to A11 times A23 times A32. And then you add that to A12 times A21 times A32. Sorry, it should be A33. A33. That's it, guys. That's my magic trick. That is my magic trick. So writing it out, it looks like it's not much of a, may not look like it's much of a trick, but when you actually perform it, it's actually simple because it's just straight through. You don't have to like overdo anything. You don't have to do any cofactor expansion or any such thing. So then I'm gonna put the first column here. So this is 2, 3, 3, and the second column being -2, -1, 0. So now I'm gonna perform this, right? I'm gonna perform this multiplication. 3 times -1 times -1 is 3. Multiply these of diagonals here. What do I get? I get 0. Multiply these diagonals here. What do I get? 3 times 3 is 9 times -2 is -18. So that's my first numbers, right? So when I put them all together, this becomes -15. And then when I multiply it on the other side, 2 -3, 2 -1 times 3, I get -6. Then I have these here. Well, 2 times 0, 2 times any 0 is 0. And I get another 0 here, 0 as well. So then what's the determinant? The determinant of A will be what? It will be -6 minus what? -15. This equals -6 plus 15, 9. Make sense? Now, I may just be making this up, right? Like the whole time, I'm just like, hey, this is determinant. You guys are like, what? Like, how can I be sure? Well, let's just check it out. So I'm gonna perform determine. I can find a determinant using the calculator as well. So I'm going to just edit my matrix, my A matrix that I have. I'm gonna write it as 2, -2, -1, 3, -1, 0, 3, 0, 3. Then I'm gonna go back and I'm gonna go to second matrix. And guess what it says on the math? The first option is determinant, DET. Then you do second matrix, you apply A, and let's cross our fingers that we get the same thing. 9, boom. So I guess we're doing the right thing. Everybody see that? So you can find the determinant using your calculator as well, but now we know how to find it actually. So Baldwin, yes, you have a question.
Professor, could you show us how to get the determinant again on the calculator?
Oh yeah, it's actually very easy.
Like the process.
Yeah, all you have to do is first plug in the matrix, the one that you want. So you want to edit it, right? So I have my matrix that I'm using right now that as an example, and then I just go back to second matrix, and under math, you see all of these different options. You can do row echelon form, which we used before already. These other options we haven't used yet. We don't really need to at the moment. You can find the transpose. This second option is the transpose of a matrix, which is kind of also easy to find yourself. But the first option you have under math is determinant. So the moment you want to find a determinant of a matrix, you can actually find the determinant of a matrix. You just have to define the matrix that you want to find the determinant of first. So first plug in the matrix that you're interested in using edit. Once you have that defined, you can use the math function underneath matrix, which is the first option there is determinant. And then you have to go to the original, like the home screen, go second matrix, and go to math, determinant, and then plug in the matrix that you're interested in finding the matrix, the determinant of, and then you do second matrix, and then you find the matrix that you're interested in, and in this case was A. But look, let's try what happens with B. What do you think happens with B? Invalid. Wait, what? What's so wrong? What's so bad about B? What's so bad about B? So you go to B, right? B is a what? B is a 3x1 matrix, which is a column vector. You can't take determinants of vectors. You can't take determinants of matrices that have different dimensions. In other words, you can't take determinants of non-square matrices. So you see how everything comes back together? So we started talking about, wait, what are different kinds of matrices? Well, there's square and there's non-square ones. So at first you're like, okay, great. But now we have things such as a determinant that can only be applied to square matrices. You can't apply them to non-square matrices. So knowing whether a matrix is non-square or square does imply more than just being that they have different dimensions. Well, with square matrices, you can find a determinant. So in other words, every square matrix has a determinant. Non-square matrices, determinants are irrelevant. They're not applicable. It makes no sense to speak of determinants when we talk about non-square matrices. So that's another thing to keep in mind. Determinants are only applied to square matrices. Okay? Makes sense? Great. Great.
Yes.
Good. Good. So now we know how to do 3x3 matrices and without a sweat, right? We don't have to sweat anymore. We don't have to do all this cofactor expansion stuff. That gets kind of crazy. So then let's do it one more time, real quick. So these numbers here, you multiply them. So I'm gonna use the colors again. These numbers here, you multiply them, right? What do you get? You get -6. And then of course I forgot, you have to plug in, you have to put the first row, the first column, pardon me, and this the second column. And then you multiply this out. What's nice about that? Hey, there's a 0. Then when you multiply these, what do you get? -4. This is a positive 12 times 2 is 24. Look at the other column, the other diagonal, you get 0. This diagonal here, you get 9. This diagonal here, you get negative. So this is 16 times 2 is -32. So these are the numbers that I care about. Of course, I want to add these together. I want to add these together. So what do I get? I get 18 when I add those together, and I get a negative 23. So then what's the determinant of A? I get -23 minus 18. So when I subtract these, I get a -41. And just to quickly repeat the matrix stuff here to find it using your calculator, I'm gonna edit the B matrix in this case. So 3x3. And the first row is 0, -3, -2, -4, -1, 1, -3, -4, and 2. So make sure we did everything correctly. I want to go and actually find the determinant using my calculator. So I use the math function, go to the first option, determinant. Then I'm going to plug in, going again back to matrix. Then I'm going to use the B matrix that I just defined. If everything went right, I got -41, which is right. So the determinant trick works. Now, is it really a trick? No, it's part of the cofactor expansion. If you apply the cofactor expansion to the matrix, this is what occurs every time. So it's not really a trick, but it looks like a trick. Alexa, no problem. I'll see you, I guess, on Wednesday. I hope you enjoyed the determinant in your dentist's office. So that's the determinant, guys. That is dedication. I respect that. Respect. Hope they're not doing anything crazy to your teeth. Okay. All right. So we got 3x3 determinant. Great. Great. I think this is a repeated question. Okay. Sorry about that. This is a repeated. I repeated this here. Okay, great. So now properties of determinants. Properties. Again, this stuff are just coming back in waves. It's like, what? I thought we're done with this elementary stuff. No, it's coming back. So remember what kind of elementary matrices we have? They're related to the they're related to the rows of operations, right? So remember we have rows, the elementary row operations. So we have 3 of them, right? We can swap rows. We can multiply row by scalar, or we can add a multiple to a row of a row to another row. So those are the 3 different kinds, right? So the elementary matrix associated with this one, I'm gonna call just E, right? The elementary matrix associated with E, when we swap the rows. The determinant, if I swap one of the rows, the determinant of this matrix, if I just swap one of the rows, the determinant is -1. Now, why is that? Well, note. What's the determinant of the identity matrix? Well, remember the identity matrix? The diagonals are all ones. You have zeros everywhere else. So a diagonal matrix, identity matrix is a diagonal matrix. And diagonal matrices have very similar properties to triangular matrices. It's just that diagonal matrices have zeros both above and below the diagonal, whereas the lower triangular, upper triangular have zeros either below or above the diagonal. But diagonal matrices have very similar properties in terms of determinants. The determinants of a diagonal matrix are just going to be the numbers along the diagonal entries themselves. And you can prove that yourself. You can see that by cofactor expansion along any row, any column in that case. So the determinant of the identity is 1. That's important. Determinant of the identity is 1. So remember elementary matrices that are associated with, for example, if I want to swap the first and second and third row of a 3x3 matrix, then what's going to be the elementary matrix? Is going to be the swapping of the first and third row of the identity matrix. So whenever I swap the rows, the entries, right, are no longer if I were to find the determinant of this guy, a -1 is going to appear. It's not going to be a +1 anymore. And that's every single time I switch it. Every single time I switch a row, determinant of is -1. Now, what happens if I multiply by a scalar? Remember what the elementary matrix would be? So if I multiply by a scalar, call it C, right? What would be an example of a elementary matrix? So for example, if I want to multiply the 4th row of a 4x4 matrix, what would it look like? What would E look like? 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 C, correct? Right, right. It's the identity matrix with the diagonal entry at the fourth entry being a C. But what's the determinant of this? It's the product of the diagonals. What's 1 times 1 times 1 times C? It's C. So if I multiply a row by a scalar C, then the determinant of that elementary matrix is C. So when I have an operation upon a matrix, when I swap the rows, I'm going to multiply by a -1. If I multiply a row, just one single row by a scalar C, then the determinant of that elementary matrix is just that scalar C. Now the interesting one though, the interesting one is when you have a multiple of a row added to another row. Do you remember what those matrices look like? So for example, if I add the second row to the third column, if I add a second row, so example, I add R2 plus R3 into R3. And let's make this a 3 by 3 matrix. Remember what this looks like? So then R2 plus R3, the second row, third column, would be something like this. Oh no, pardon me, it will be the other way. It'll be like this. Yep. Because these first two rows, they leave the first two rows of the matrix by itself, and then the third row would be the second row when you do the matrix multiplication. You take the rows, the entries in the second row, and you add it to the entries in the third row. But what do you notice about this matrix? The matrices for the elementary matrices for any of the elementary row operation that does this, that adds a multiple to another row. What are all of them always going to be? So you see here, these are like just operation, like switching the rows of an identity matrix. This will always be a diagonal matrix, always diagonal. This will be always what? What kind of matrix will this always be?
Triangular?
Yes. It will always be either upper or lower. Right? It will always either be an upper or lower triangular matrix. But wait, what do we know about triangular matrices? The determinants are always what? The product of the diagonals. But what's 1 times 1 times 1? It's 1. So I just noticed that we're not gonna have enough time to go over everything that I want to go over. So I'm gonna extend the homework for today till Wednesday. So we're gonna go finish with this on Wednesday. So I'll do that. But what do we come away with this? Is that the operations that we apply, that we can apply to matrices, right? Either swapping rows, multiplying by a scalar for one row, or multiplying a multiple by another row, right? It has certain effects. It affects the determinant. So if I apply just one row, swapping one row, I'm gonna multiply by -1. You'll see what I mean by that. If I multiply a matrix by a scalar, then I'm multiplying that matrix by whatever that scalar is. And if I add a multiple to another row, from one row to another row, then actually the determinant is unchanged. That's really cool. This step is really cool that I can add multiples of one row to another row and the determinant doesn't change whatsoever. It's the same. And why is it the same? Well, we just kind of showed you, right? Every single time we apply this, the matrix that we're applying to it, the determinant of that matrix is always one. So this step here does not affect the determinant of the overall. It doesn't really affect the determinant. Swapping rows doesn't affect the determinant. There's a multiple -1, and when you multiply by a row by a scalar, you do affect the determinant by that scalar. But when you add a multiple of a row, it doesn't affect it. Okay, so then I'm just going to write a few more of the properties. So we've seen a couple already. We know that the determinant of the identity is 1. The determinant of a matrix, the transpose, is actually equal to the determinant of its original. And that should make sense because of the cofactor expansion. Whether I do rows or columns, it doesn't matter. So if I transpose a matrix and it changes rows to the columns and columns to the rows, it's not going to affect the actual determinant procedure or computation. What else do we have? We have, so the determinant, so if a matrix has 2 rows, has at least 1 row or 1 column of zeros, then, sorry, if a matrix A has at least 1 row, 1 column of zeros, then determinant of A is 0. What else? Oh, yes. The determinant of A inverse is equal to 1 over the determinant of the original matrix. And I'll leave you with one more. Yeah, the determinant of a product of matrices is equal to the determinant of one of them multiplied by the determinant of the other. So there's a few more no problem. So all we've been doing so far at the end is we just talked about the properties that exist with determinants. So we've done a lot of computation throughout the whole lecture today. And we're also going to slowly start to see a bit more of a theory behind it. And so a lot of these properties, there's a theory, right? How do we, well, we can prove this very easily. Determinant of an identity is 1. We can prove this very easily, that the transpose, determinant of a transpose is equal to the determinant of the original function. We can prove this also very easily. But then now, this one is a little bit difficult, more complex, I should say, to prove that the determinant of a product of matrices is equal to the determinant of each matrix individually when you multiply those two numbers. So yeah, I guess I'll stop here. So again, I'll stop here. I'll extend the homework that's due tonight for Wednesday. So we'll finish probably like within the first hour. So we'll do this. We'll finish the first hour. We'll probably finish before the first hour on this stuff. So your homework number 5 will be due on Wednesday.